All right, let's take a look at problem number 6. For 6, we're to find the x-coordinates of the points of inflection for g on the interval -6 to 5 and those of h on the same interval. Okay, so remember this is a graph of um, f. We concluded earlier that since the integral of f is g, f is basically the derivative of g. Okay, so this is the graph of f, and based on this expression right here, this basically implies that f is equal to g prime. Just by differentiating both sides, you can get f isolated, and then differentiating g, you get g prime. All right. All right, so let's keep those points in mind for number 6. Now, before we find the points of inflection, let's go over the different ways to find the points of inflection of a function, okay? So, let's go over the rules. So let's say if you're dealing with, let's call this points of inflection, POI, to get the points of inflection. For f, if you're given the graph of f, how do you find the points of inflection? C is a point of inflection if f changes from concave up to concave down, or it changes from concave down to concave up. Okay, so if there's a change in concavity on the graph of the original function, then you have a point of inflection at that point where the concavity changes. Now, what if you're given the first derivative? Well, for the graph of the first derivative, c is a point of inflection if um, f prime changes from increasing to decreasing, or decreasing to increasing at c. Okay, so let's put at c here, and then let's put at c here. So increasing and decreasing is when you're looking at the graph of the derivative. Concave up or concave down is when you're looking at the graph of the original function. Now, the second derivative can also tell us the concavity, the point of inflection too. So f double prime, for f double prime, c is a point of inflection if f double prime changes from. Now, if f prime is increasing, what does that tell us about the derivative? If a function is increasing, its derivative is going to be positive, right? So if f double prime changes from positive to negative, okay, if there's a sign change in the second derivative, that basically means there's a change in the concavity, which means we have a point of inflection. Or if it changes from negative to positive, this happening at c, then we have a point of inflection there. So these are the three ways you can determine the point of inflection of a function. So first of all, we are to find the point of inflection of g. Okay? So to find the point of inflection of g, we are provided with the graph of g prime. So out of these three approaches here, which of them are we going to use? We have the graph of the derivative, so we're going to be using this approach right here, approach 2. Okay, so where is this graph? What does it change from increasing to decreasing? That tells us where we have a point of inflection. So let's look at this function right here. For this function, we know that from -6 to 5, it's increasing. From -5 all the way to 0, it's decreasing on this interval. And then from 0 to +3, it's increasing. Well, actually, from 0 all the way to +5, it's increasing. So we have changes in increment or decrement at -5 and at 0. All right? So let's write down our answer and justification. So we're going to say G has points of inflection of inflection at x equals -5 and 0, at x equals -5 and 0, because why? Because g prime changes from, let's write a complete word here, increasing to decreasing, at x equals -5, at x equals -5, and it changes from decreasing. Let's make sure that what I'm saying is correct. So change from increasing to decreasing at -5, and then g prime change from decreasing to increasing at x equals 0. So it changes from decreasing to increasing at x equals 0. So this is sufficient explanation as to why we have a point of inflection for g at these 2 points. Okay, so this is for g. Now let's look at h. Okay, so we're looking for the points of inflection for h. That's the second part right there. So if we're looking for the points of inflection for h, okay, so actually, let's make that f. I meant to say f, not h. Okay, so we're gonna look for the points of inflection for h. All right, so now since we're looking at the graph of f, um, which of these 3 approaches are we going to use to determine the points of inflection of f? Since we're given the graph of f, this right here is the graph of f. So we are going to be using approach number 1, okay? So when you're given the graph of the function and you're asked to find the point of inflection, all you just do is you're looking for the points where the concavity changes, all right? So let's look at this graph right here and talk about where the concavities are for the different intervals. So if you look at from -6 to -5, on that interval, the function is concave up, as you can see. From 5 to 4, it's neither concave up nor down. Okay, so there isn't any concavity there, so that doesn't really count. On this point, from -3 all the way to 3, on that interval, the function is concave up. And then from 3 to 5, it changes to concave down. So where are the points where concavity changes? The only point where concavity changes is at x equals 3, because it changed from concave up to concave down. All right, so let's write that down. F has a point of inflection at x equals 3, because the graph of f changes from what? It changes from concave up to concave down at x equals 3. So that's basically why you have a point of inflection for the graph of f at x equals 3. All right, now let's take a look at the next problem. For problem number 7, we are to find the average rate of change of f on the interval -6 all the way to 5. Okay, so let's write down what the formula is for the average rate of change, and then we're going to apply it to this situation. So for problem 7, let's write down the formula for the average rate of change. So average ROC, let's call that rate of change of a function f, is basically f of b minus f of a divided by b minus a. Okay, this is the average value of the derivative of f, is the same thing as the average rate of change of f. Okay, All right, so we're looking for the average rate of change of the function on the entire interval. So the average rate of change of f, I like to call it delta f, delta um, x on the interval from where to where? From -6 to 5. This is our a, okay, and this is our b. It's simply going to be f of b. F of b is 5 minus f of a, which is -6, divided by b minus a. 5 minus -6, which makes it a plus 6. So what is f of 5? We just simply consult our function and determine the output value when the input is 5. So when x is 5, our output is 2. So we can see from this point that f of 5 is equal to 2. And then from this point, we can see that f of -6 is what? The output is 0. F of -6 is 0. Okay? So let's apply that here. F of 5, we determined it was 2 minus f of -6 was 0 divided by 5 plus 6, which is 11. So our final average rate of change is 2 over 11. Okay, so this is the slope of the secant line. Now the second part of question 7 says that is there a C that satisfies the conclusion of the mean value theorem in this interval? Is there a C on the open interval from -6 to 5 that satisfies the conclusion? Well, let's look at the hypothesis first. The hypothesis requires two conditions. The function has to be continuous, which it is on the entire domain, and it must be differentiable on the entire domain. So is the function continuous? Yes. Is it differentiable? Absolutely not. Differentiability fails at 5 because you have a corner here. It's kind of like a cosp and a corner together, but I just call it a corner. And then you have a corner here. You have a vertical tangent here, an undefined slope. So since you have differentiability failing at more than one point, at a point or more in the interval, then that means that the hypothesis of the mean value theorem has been violated, hence there's no C that satisfies the conclusion. Okay? So if you have a function that is differentiable and continuous, then you can advance to the conclusion. But if it's not differentiable at any x value, then it automatically violates the hypothesis of the mean value theorem. Okay, so our answer is there is no C, or C's, it could be more than one, on the interval, on the open interval -6 to 5, that satisfies the conclusion of the mean value theorem. And we have to state the reason why. We can just say, why is that the case? Well, it's because since the function does not satisfy the differentiability piece of the hypothesis of the mean value theorem. Okay, in order for you to conclude, to have a C that satisfies the conclusion, the two hypotheses, continuity and differentiability, must be satisfied. Just note that the continuity must be on the closed interval. It has to be continuous on this closed interval, continuous here, and it must be differentiable on the open interval. So endpoint differentiability is of no consequence. It must be differentiable on the open interval. Okay, because we know that differentiability implies continuity, but since the continuity is on a different interval, that's why we have two conditions that must be satisfied. Now, since this graph that we just looked at violates the second condition, because we had 3 points where the function is not differentiable, we cannot have a conclusion to the mean value theorem. All right, so that's that. Okay, now let's take a look at the last question.